Welcome to the next teaching unit in the chapter on crystalline silicon solar modules. This unit is about the production of solar cells. In the last unit, we dealt with how first silicon crystals and then wafers are made from raw material quartz sand. This unit is about the next step on the way to the finished solar module, the production of solar cells from wafers. In the last chapter, we dealt with various losses that reduce the efficiency of a solar cell. Remember, one of the biggest loss factors is reflection, which can cause up to 36% of the incident light to be lost. To reduce the reflection losses, the surface of the wafer is therefore textured. Shown here is a texture of uniform pyramids. However, the pyramids only look so uniform if they were made in a laboratory. In industrially manufactured solar cells, the pyramids are usually of different sizes and randomly distributed. Here you can see the example of a multicrystalline wafer before and after the texture. The texture makes the surface of the wafer appear darker due to the lower reflection. In addition, the wafer becomes duller. In the case of multicrystalline wafers, the grain boundaries are now less clearly visible. These textured wafers are now usually made of weakly p-doped silicon. You remember, the silicon is already mixed with a dopant during crystal growth. Gallium is usually used for p-doping today. However, as we already know, for a solar cell we need a p-n junction, that is, p-doped and an n-doped layer. The n-doped layer is still missing at the moment. To produce the n-type layer, the wafer is heated in an atmosphere with gaseous phosphorus compound to a temperature of about 850 degrees Celsius. The phosphorus atoms can diffuse into the wafer due to the high temperature. The result is a thin, a few hundred nanometer thick layer in which there are more phosphorus atoms than gallium atoms. Because each phosphorus atom also contributes a free electron and the holes are overcompensated, this area is no longer positive but negative conductive. The result is an N+ region, a region with high electron conductivity. By these means, we have now produced an NP junction, that is, an N+ emitter and a P base. As mentioned in the teaching unit on loss mechanisms, there is an increased recombination of charge carriers on the surface at defect sites that are located here. We have also already learned how to reduce this surface recombination, namely the application of an insulating layer that passivates the surface. The functioning of this passivation layer can be best explained with the help of a band diagram. First, let's look at the band diagram of N-silicon with a surface that is not passivated. The charge carriers reach the surface unhindered by diffusion. There, they recombine very quickly because there are lots of energy levels of vacancies in the middle of the band. With passivation, which consists of an insulator like silicon nitride or silicon dioxide, a high potential level is created on the back or on the front of the solar cell in both valence and the conduction band. The resulting electric field drives both holes and electrons back into the silicon semiconductor. The passivation acts like an electron and hole mirror, driving all charge carriers away from the surface. For the minority, in this case the holes, this brings the desired effect. How we bring the majorities, in this case the electrons, to the contacts, we will explain in a moment. But first, let's look at the optical optimization of the solar cell. As already mentioned, the N+ emitter is more highly doped than the P base due to the process of diffusion. However, the higher doping also reduces the lifetime of the photogenerated minority charge carriers. If the doping is very high, the minorities can no longer reach the p-n junction and recombine. We need to know that a large part of the light is absorbed in the first micrometers of a solar cell. As a reminder, here is the illustration of the absorption depth in silicon. This figure was explained in detail in the teaching unit on loss mechanisms. The absorption depth in the blue region is only a few micrometers. In order not to lose the charge carriers generated in the first micrometer through recombination, the emitter is therefore made quite narrow. These considerations lead to the standard structure of a solar cell today. The 150 to 200 micrometer thick weakly p-doped base is located on the underside, and an approximately 0.5 micrometer thick n-doped emitter is located on the top. An antireflective layer is applied to the emitter, which reduces reflection losses. At the same time, this layer leads to a passivation of the surface. Hence, the layer fulfills two important tasks, an electronic and an optical one. For silicon solar cells, silicon nitride is usually used here, since the refractive index of the material with N equals 2 is optimal for an antireflective coating of silicon. Here you can see the reflection of silicon with and without texture, depending on the wavelengths. The texture already reduces the reflection considerably, but not completely. As we have learned, with a suitable refractive index, the reflection for a certain wavelength can be prevented by choosing the right layer thickness. For solar cells, the antireflective layer is optimized for a wavelength of about 600 nanometer, since this is where the radiation maximum of the solar spectrum lies. With such a layer, the reflection at 600 nanometer is reduced to 0. The reflection is also significantly reduced in the remaining spectral range. The reflection curve shown represents an antireflective layer optimized for 600 nanometer on non-textured silicon. The reflection is strongest in the blue spectral range. This is also the reason for the classic blue color of solar cells. If the antireflective layer is applied to a textured surface of silicon, this curve applies. Here the reflection in the blue spectral range is already significantly reduced and the solar cell appears in dark blue. Here you see a textured wafer before it is coated with silicon nitride. The brighter the wafer appears, the more light is reflected. On the right side you see the same wafer after coating with a 16 nanometer thick silicon nitride layer. While the raw wafer has a silver gray color, it appears blue and much darker after coating. Let's now look at what happens when we apply contacts to the emitter. The passivation layer on the emitter is insulating. It therefore prevents the charge carriers from reaching the contact fingers. Therefore, the contact fingers must penetrate the passivation layer in order to have direct contact with the emitter. But now we have the same problem again as at the interface between the contact fingers and the emitter, as before at the surface on the front side. The unsaturated bonds in the crystal lattice lead to increased recombination here. In order to reduce the recombination at the transition to the contact, the emitter is more heavily doped. However, since excessive doping of the emitter must be avoided due to the lifetime of the minorities, this higher doping is only carried out selectively, directly under the contacts. This is done by burning in additional phosphorus with the help of a laser at the point where the contacts are applied. This means that additional phosphorus can diffuse into the emitter at this point due to the local heating by means of the laser light. The higher doping is represented here by N++. This so-called selective emitter is now state-of-the-art and is implemented in all modern solar cells. The losses through the contacts were also dealt with in the so-called teaching unit on loss mechanisms. We saw that the contact grids consist of SiC bus bars and many contact fingers. When optimizing the contact grid, the ohmic losses in the contacts in the emitter and the shadowing losses are weighed against each other. For many years, the standard solar cell was manufactured with 2 bus bars. In recent years, the number of bus bars has steadily increased. Today, most solar cells are manufactured with 9 or more bus bars, or even with wires as bus bars. We have now dealt with the front side of the solar cell. But what about the back side? Of course, surface recombination occurs on the back side of the solar cell just like on the front side. The structure here is therefore quite similar to that on the front. First, a passivation layer is applied to reduce surface recombination. This layer works in the same way as on the front. Since the passivation layer is insulating, it is punctured by contacts made of aluminum. Just like on the front side, recombination also occurs on the contacts on the back side. Therefore, higher doping is also applied here at certain points. This is done by diffusing the aluminum atoms in a short high-temperature step. Similar to boron or gallium, aluminum is an acceptor atom that provides holes. The higher doping here is characterized by P+. This P+ doping is also called back surface field. The functioning of the back surface field can also best be explained with the help of a band diagram. We can understand the transition between P and P+ layer similar to a p-in transition or p-in junction. Holes flow out of the highly P+ layer into the P region due to the concentration gradient, leaving behind stationary negatively charged atomic hulls. The resulting electric field is visible in the band diagram through a further potential step. It drives incoming electrons back into the semiconductor and prevents them from reaching the contacts. The back surface field thus acts as an electron mirror. More effective than a back surface field, however, is the use of a passivation layer that covers most of the surface of the back of today's solar cells. The mode of operation is analogous to that of the front side. The band diagram shows the bands in the p-doped silicon as well as the bands of a very high band gap of the insulating passivation layer. Due to the significantly larger potential step between the conduction band in the p-silicon and the conduction band of the passivation layer, a much stronger electric field is created than in the case of the back surface field. This results in a much more effective electron mirror than in the case of the back surface field. Today's standard structure of a solar cell therefore consists of an N plus P silicon junction that is covered on both sides with passivating layers. This type of solar cell is also called a Perc solar cell. Perc stands for passivated emitter and rear contacts. The name thus refers to the passivation on the front and rear sides. Because of the more effective electron mirror, Perc solar cells have a higher efficiency than solar cells with a full aluminium rear contact, and thus a back surface field on the entire back of the solar cell. The technology with a full area aluminum back contact was state of the art until 2018. But in 2018 to 2019, the industry switched to Perc technology. The Perc structure now also enables the so-called bifacial solar cells without any problems, as it does not contain a full surface rear side as previous solar cell designs with a full surface aluminum contact. Bifacial solar cells can convert sunlight falling on both the front and the back of the solar cell into electricity. The structure of the contacts on the back of the bifacial solar cell is largely the same as on the front. In addition, an antireflective layer is applied as on the front side. This design makes it possible to efficiently use light that is incident on the back of the solar cell. This is particularly important for ground-mounted systems where light is reflected from the ground to the underside of the PV module. I will summarize the most essential points of this lesson. In this lesson, we learned how a standard silicon solar cell is constructed today. The texture of the silicon surface significantly reduces the reflection losses of the solar cell. In a high temperature step, phosphorus diffuses into the silicon wafer and overcompensates its gallium doping several times. This then results in an N plus P transition or junction. Modern solar cells are coated with various materials to reduce losses in the solar cells, passivation layers to reduce surface recombination, and these layers also serve as antireflective coatings to reduce reflection losses. In addition, recombination losses are reduced by heavy doping under the contacts. I thank you for your attention.